And so attendance today is a little bit less than impressive. Should we do a pop quiz or something, just to make sure that people have incentive, or it's just people are tired from the week? How was the midterm exam? It's not that bad, I think.
I think this one went a lot better than the past ones, in my opinion, for me.
Yeah. Okay. Well. Recording. So keep in mind that the final exam, of course, is going to have conceptual questions from the entire semester. But for the calculational problems, you're going to have the emphasis on the material from chapter 27, which is interference in diffraction of light, as well as the other chapters that were in midterm theory. So this is chapter 24, electromagnetic waves. Chapter 25, mirrors. Probably mirrors are trivial, so maybe not calculational problems from chapter 25, but you should have again lenses. So you're going to have again probably a question about eyeglasses, draw a diagram, form an image from converging, diverging lens, things of that nature that you actually should already know. Just don't forget them. The final exam is just in about 2 weeks or so. In addition to that, we're going to have mostly conceptual questions from modern physics, chapters 29, 30, 31, and if we get to chapter 32. We're not going to talk about special relativity. Chapter 28 is out of the curriculum because special relativity doesn't have real applications in almost any technical field, first. And second, it could be quite confusing to talk about time dilations and length contractions, and it's going to be confusing. So I don't want people to get confused with special relativity. But the other chapters from modern physics have some practical applications, and we're going to talk about them. So we're going to briefly describe section, let's say, devoted to particle wave duality, which basically tells you a stream of particles also can be treated as if you have electromagnetic wave like light. So you're going to have questions related, mostly conceptual or a single line arithmetic type of questions related with particle wave duality, Heisenberg uncertainty, resolving power of optical instruments, material that we're going to talk about today. And especially, you're going to have actually a real calculational problem related with carbon dating. So this is somewhere chapter 30 or chapter 31. So we have to learn how to do carbon dating because carbon dating is done with biological materials, biological samples. So many of you are biomedical majors. And also carbon dating gives you an idea how you do dating of, let's say, geological formations. One way to do very accurate dating is using isotope fractions, isotope ratios of some isotopes that are with known long half lifetimes. So this is the plan for the remaining 2 weeks. And today we're just going to talk about interference and diffraction of lights again, because we haven't covered all the details of that chapter. Okay, any remarks, questions, and issues? Well, in that case, let me summarize where we stand so far. So we started chapter 27 with the double slit experiment. This is classic experiment done in, well, even before 20th century. It is 2 slits separated by a distance d between them. And you have incoming wavelength light with wavelength lambda, incoming light, and a screen that has to be at a distance much larger than, let's say, the separation between the slits and the width of the slits. So I should draw it somewhere here, but of course we don't want to occupy the entire board, so I'm just going to draw it here and to imagine that it is on the other end of the board. But in any case, what you observe is that the light forms a typical interference pattern. So you have central bright fringe, followed by a dark fringe, and after that a secondary bright, and so on, symmetrically on all sides of the central bright spot. So it is a typical interference pattern. The interference is interference between the light that comes through the first and the light that comes through the second slit. And you can write down the condition for constructive interference, bright spots, or destructive interference, dark fringes. It is based on the fact that the 2 light rays, the light ray that come through the first and through the second slit, they travel different paths, different lengths of the paths that they travel. So the first one is going to cover this distance, this path. The second light ray is going to cover this path. And therefore, the path difference is going to be this length right here. And now look, if you're thinking about what is the location of the bright fringes, at what angle with respect to the central dashed line is that, so angle theta, you can figure out the location of all bright fringes by looking at this triangle and expressing the path difference in terms of the distance between the slits D and in terms of the angle theta. So the angle theta is the same for this triangle as the angle at which, let's say, the first or any other bright fringe appears. So looking at this triangle, which is going to be almost right triangle in case if the screen is very far away. And in that case, the size of the path difference between the 2 interfering light rays is going to be given with d times sine of the angle theta. And therefore, the condition for a bright fringe looks like this. d times sine of the angle theta is equal to integer number, let's say m, times wavelength lambda, where m is either 0 or 1 or 2 and so on. In other words, the way we write this is the angle at which bright fringes occur has sine equal to m times lambda divided by d, where m is integer number, positive or 0. In a similar manner, the location of the dark fringes is due to destructive interference, and the condition for destructive interference is semi-integer number of wavelengths. So, singular expression for the condition for destructive interference. Yes.
So the first sine of theta equation is for the
Look,
not the opposite of the constructive.
constructive interference, yes. The angle at which bright fringes appear. Constructive interference. And this is the condition for destructive interference, the angles at which dark fringes are going to appear. So the double slit experiment is a classic experiment. It is, we don't usually do it in the introductory lab that you're taking, but just because it is tricky to work with, oh, you're doing it.
We actually did, yeah.
Oh, you did this, really?
Mhm.
Okay, wow.
It was very difficult. It was the worst.
Well, working with slits that are so closely separated by such a short distance, and I don't know, do you do it with lasers or with what? What was your
light source.
But not a laser, was it?
We just put a filter over the
Yeah.
light source.
Okay, so the filter just gives you monochromatic light, so single wavelength. But laser is probably even easier and cheaper. Right? Lasers now are not expensive. And you have seen the double slit interference pattern. So here is this right here is double slits, and let's see if we can observe the interference pattern from double slits like this. Maybe we need darker. And so let's see. Well, you see, it is not perfect with red, but let's try with green. Oh, nice interference pattern. You see it, multiple bright and dark spots are visible. So why are we spending this amount of time talking about double slit experiment and how the picture looks, and on top of that, so why do we spend this amount of time? Well, multiple reasons. First, theoretical. As far as we know, well, not as far as we know. So at least in the past, interference phenomena were clear indication of wave nature of the system that you're working with, in this case, light. So this just is a proof that light has wave nature. And in the link that I gave you at some point, you were doing, that link was about a simulation in which you can do this double slit experiment with light, well, kind of light, simulated light, or with electrons, or with surface waves on water, for example. And the interference pattern in all those cases is the same. The only trick is that you have to choose the separation between the slits and the size of the slits appropriately. Otherwise, you wouldn't be able to get visible interference pattern. So, interference is the world of waves. This is why we deal with interference from two slits. And two slits, of course, is less complicated than multiple slits. The second reason why we deal with interference from slits is that we use them in practical applications. So look, in the case of two slits, one wavelength of light is going to give you bright spot at this position. A different wavelength is going to give you a bright spot shifted in a different place. Therefore, if you have incoming light that is a mixture of different wavelengths, the interference picture is going to separate the wavelengths from each other. And you're going to see the constituent wavelengths of the incoming lights. And this is what is important in the case when you're doing spectroscopy. You're trying to figure out the composition of some sample. And, well, looking at the spectral lines emitted from that sample when you heat that sample, burn it, or whatever you do with that sample to excite it. Looking at the interference pattern of that light, you figure out the spectral lines and therefore the composition of your sample. What kind of compounds, what kind of elements are present there. Now, in practice, instead of using two-slit type of setup, you use multiple slits, hundreds of slits of the same, with similar separation like here on the board. And the reason why you, in other words, you use what we call diffraction grating. And why do we do that instead of two slits? Because with multiple slits, you're going to get a brighter interference pattern. It's going to be easier to measure and to see it. Also, diffraction grating, those multiple slits are going to have more narrow, bright fringes. And therefore, you're going to be able to separate different wavelengths better by a larger distance. So we're not going to prove that a diffraction grating consisting of multiple slits is going to give you a more narrow and bright interference pattern, but it is clear, right? If you have more openings, you're going to get a brighter light coming on the other side of the slits. And also the fact that the slits are going to be, the interference pattern is going to consist of more narrow maxima and minima is due to the fact that, well, the constructive interference condition can be satisfied for this number of slits, but not for infinitely large number of slits. So you're going to lose the condition, let's say, for constructive interference after some number of slits. You're going to recover it again later on and so on. So it's going to be a little bit of messy picture, and this is why it is not considered in our textbook, and we're not dealing with it. Okay, the second type of questions in chapter 27 is about diffraction from a single slit, let's say. So if you have a single opening with width W, and let's say that you have light with wavelength lambda coming in, Again, on a screen that is located very far away from the single opening, you are going to be able to observe a picture similar to the interference pattern from two slits. So you're going to see a central bright maximum, followed by dark fringes and secondary maxima with smaller intensity. So here is secondary maxima with reduced intensity. Of course, the wavelength and the width of the opening have to be appropriately chosen in order you to be able to see the interference pattern. And in the case of a single slit, you can demonstrate that most of the intensity of the light that makes it through is contained within the central bright interference spot. So the secondary fringes, bright fringes, carry very, very small amount of intensity. And as a result of that, you don't want to figure out for practical applications, you don't want to deal with the secondary maxima. You basically deal only with the central maximum. And we demonstrated that the angle at which the first dark fringe appears, this angle theta, the location of the first dark spot, is given with an angle equal to lambda divided by the width of the slit, the single slit. In other words, most of the intensity of the light that makes it through this single slit is going to be confined within this 2 theta angle. And well, then the next detail is to figure out what is going to be the diffraction picture that you're going to observe if instead of a rectangular slit here, if you have a circular opening with a diameter d. And it can be shown that the angle at which the first dark ring appears is going to be given with a similar formula like a rectangular slit with a small correction. And the correction is the number 1.22 lambda divided by the diameter of the circular opening. So this is the formula that we're going to use when analyzing resolving power of the human eye or optical instruments like telescopes, scopes of different types. Because, yeah. Now, of course, keep in mind that the same interference or diffraction pattern can be observed if instead of an opening, a hole, a slit, multiple slits, if you have barriers, the same pattern is going to be observed both in the light that is transmitted and in the light that is reflected also. And we said here it is, you observe an interference pattern generated by the light that is reflected from the grooves of a, let's say, DVD or CD disc. You see those color rainbow colors reflected at different angles when you appropriately point the light with respect to the DVD disc. Okay. So what we're going to, so the last section in chapter 27 deals with interference from thin films. So what is this? Well, if you have observed that if you have a film of oil, let's say, floating on top of water, when you look at it from appropriate angle, you see rainbow colors, rainbow colored surface. This rainbow color observation is due to interference of this following type. So consider, let's say that here is the, let's say air is this first medium with index of refraction n1 equal to 1, followed by a thin, and of course we have to exaggerate the thickness of oil, let's say with index of refraction 1.3, 1.2, let's say. And the last layer is, let's say, water, which with index of refraction n3 equal to 1.3, let's say. Let's work with those numbers just for the sake of the argument. Actually, in this interference picture, the numbers matter. Which number is larger and which number is smaller matters, as you are going to see in a minute. Now, for simplicity, we're only going to work with light rays that come in almost perpendicular to the surface. So light ray almost perpendicular. But if I draw perpendicular light ray, it is going to be reflected, refracted. Light rays are going to be on top of each other, and you're not going to see them well. So this is why instead of perpendicular light rays, I'm going to draw an incoming light that is coming under some certain angle. You just have to imagine that this angle is practically incident angle equal to practically zero for simplicity. But the idea is the same for finite non-zero angles of incidence. So here is the normal to the first surface. So when the light encounters different medium, part of the light, of course, is going to get reflected this way. And part of the light intensity is going to penetrate the film. In other words, it is going to be refracted. It is going to hit the surface of the water. And well, from the surface of the water, you're going to have another reflection. And of course, you're going to have refracted light ray, but I'm not interested in this light ray, so I'm not even going to draw it to keep the picture easier to figure out. Okay, so now this reflected from the second surface light ray, let's say it comes this way. It reaches again the first interface, the first surface. Again, you're going to have some reflection. I'm not interested in that reflected light ray, so I'm not going to draw it. But you're going to have a refraction from this first surface, and the light ray is going to come out like this. Let's say that the thickness of the film is T, some small number, usually of the order of a few hundred nanometers usually. Now look, you have two light rays, light ray number 1 and light ray number 2, that are practically on top of each other, right? We're talking about almost normal incident original light ray. Therefore, 1 and 2 are going to be almost on top of each other and almost perpendicular to the surface, but on top of each other. And when you have two light rays with the same wavelength, they're coherent because they're born by the same original source, this one. They are coherent and the same wavelength. What do? They interfere with each other. And if that interference is constructive, you're going to observe a bright light. So here is the observer right here, looking at those, seeing those two light rays. If they fulfill the condition for constructive interference, the observer is going to see a bright spot. So let's assume that the incoming light is a single wavelength, just again for the sake of the argument. If the two light rays interfere destructively, the observer is going to see nothing. He is going to see dark. Instead of any reflected light ray, nothing is going to get reflected. Now let's write the condition for constructive interference, let's say. Well, the condition is that the path difference between the paths covered by the first and the second light ray are equal to integer number of wavelengths. So here is the path difference between them is exactly this length. And since we're talking about normal incidence, this length is going to be 2 times the thickness of the film. So condition for constructive interference is 2 times the thickness of the film to be equal to integer number m of wavelengths, where m is 1, 2, and 1 of the integer numbers. Well, it could be also 0, not for the setup that I have, but let's also include the 0. And the 0 doesn't mean much for this setup, but for later on, it's going to be needed. Now, one correction. Actually, several corrections, two corrections. So, first, this wavelength in the formula is not exactly the wavelength of the light in air, but it is going to be the wavelength of the light inside the film. And I think that last week, or no, on Monday, in Monday's class, we proved that once the light enters a different medium, different from air, its wavelength becomes reduced by a factor of the index of refraction of this medium. So when the light enters from air to oil, its wavelength is reduced by a factor equal to the index of refraction of oil in this case. In other words, in this formula, I must have the wavelength of light in the film, So this is the condition for constructive interference. The observer to see a bright reflected light. And similarly, the condition for destructive interference is that the path difference of the two light rays should be semi-integer number of wavelengths. Again, m is 0 or positive integer number. So this is the condition for destructive interference for dark, no reflection. The reflection got cancelled out. So the first detail was that we're always going to work in this formula, always going to work with the wavelength of the light in the film, inside the thin film. The second trick is to realize that when the light is reflected from a medium with higher index of refraction, higher than the index of refraction from which the light comes in, the light experiences a shift of half a wavelength. So here the light comes in, and this one is shifted by 1/2 wavelength. But in our case, when our numbers are like this, the light that eventually goes through the to the oil is also reflected by a medium that has high index of refraction, water, than the oil. And the result, this one is also shifted by half a wavelength. The two shifts cancel each other, and I didn't write them at all in the, right? This shifted half a wavelength, the other one shifted half a wavelength. There is no any relative shift between them, so I didn't put any indication that there is a shift like this. However, if the numbers were different, let's say if this was oil with index of refraction 1.5, then this light would experience half a wavelength shift in the case of reflection, while the one that goes in the oil is not going to experience it. And in that case, I'm going to have the following situation. 2t minus 1/2 lambda output lambda prime is equal to m times lambda prime for constructive interference, and 2 times minus 1/2 lambda prime is equal to m plus 1/2 times lambda prime for destructive interference. This is when one of the light rays experiences half a wavelength shift and the other one doesn't. So in the homework assignment, you have different situations and you always have to look at the numbers. The indices of refraction of the two media with respect to each other. Again, the rule is that if the second medium has higher index of refraction than the first one, and it is not a metal medium, it has to be something non-metal, the wavelength of the reflected light ray is shifted by half a wavelength. So when you look at the homework assignment on chapter 27, which is due on Monday, you're going to encounter those type of issues. And and we're going to have examples when you ask for those. Yeah.
Could you go over number 16?
Problem number 16 from the homework assignment is a problem that actually is exactly asking for this. So let's look at this. Problem number 16, example of interference from thin films. And actually, here is a simple way to demonstrate interference of from thin films with this simple, it is a two-layer two layers of glass separated by a small gap, air gap. And when you look at appropriate angle, you see rainbow colored rings. So I'll pass this around. You're the only one here, but you can pass them. And you, of course, everybody has seen oil floating on the surface of water. So problem number 16 is exactly the situation that we described. So here is, you have air, index of refraction N1 equal to 1. After that, you have oil with index of refraction that is not given. So we have to be careful. But they say that, assuming that, okay, the refractive index of this oil is larger than the index of refraction of water. So here you have water, and 3 equal to 1.33 for water. And here you have oil with index of refraction larger than the index of refraction of water. So now the unknown thickness of the film is T. And again, here is an incoming light ray. So in this problem, first you have incoming light that is 640 nanometers in vacuum or air. So 640 is probably somewhere of the red part of the spectrum. So you have incoming red light with index of with wavelength lambda equals to 640 nanometers. So once this light ray, so of course you're going to have reflection, is the first reflected light ray, and you have a refracted light ray, but once that 640 wavelength enters the oil, its index of refraction, its wavelength changes to lambda prime, equal to lambda divided by the index of refraction of the oil. Yes. And after that, again, you have reflection this way and refraction again. And here are the two interfering light rays. Light ray number 1 and light ray number 2. Of course, normal is here needed also to show that. So they say that under this condition, the thickness of the film is such that you observe destructive interference. In other words, you don't see any light reflected. Light ray number 1 and light ray number 2 cancel each other. They're out of phase. They're in opposite phase. They cancel each other. Well, the condition for this cancellation is this. The path covered by the ray that enters the oil is 2 times T larger than the path covered by light ray number 1. So this path difference has to be equal to integer number m of wavelengths in oil. And now let's think about this 1/2 phase shift, 1/2 wavelength shift. Well, the first light ray reflected from index of refraction larger than 1. So this one is going to experience a shift of 1/2 a wavelength. The second one, when it is reflected from this one, from this surface, they say that N3 is smaller than N2. Therefore, it is not going to experience half a wavelength shift. And therefore, you have to take into account this half a wavelength shift by subtracting lambda prime divided by 2 due to this additional wavelength shift of the first light ray. Yes.
So if it was the other way around, and would you be subtracting it?
So
from the other side of the equation?
if instead of, let's say, if this one, if this was not the equation, the case, you would have half a wavelength shift here and also half a wavelength shift here, and eventually they cancel out, right? If I subtract, let's say, 1/2 lambda prime from both sides, they cancel out, so nothing is going to be present in that case. But this is not what they say here.
Is there ever a case where one of them is shifted, the other isn't, but you subtract it from the other side of the equation?
Yeah, you can, look, it doesn't matter if you say plus or minus, but if you say plus, you have to start here with integer numbers, also negative. Integer numbers are going to be allowed if the numbers work out right. If you say minus, you don't need to deal with negative integer numbers. So this is what I kind of, this is. Okay, so this is the condition that they describe in the first 2 sentences of the problem. So from this condition, they say one more thing. They say one more thing. They say that the film has minimum non-zero thickness. This means that you have to say that this integer number is equal to 1, because 1 is the minimum non-zero integer number that satisfies this condition. Or does it? If you allow, it could be 0, right? It also could be 0, because if it is 0, this goes to the other. So if this is 0, if m is equal to 0, on the right-hand side of the equation, you have 0. And if you move this term to the other side with positive algebraic sign, you're going to have 2 times thickness is equal to lambda prime divided by 2, which is okay. In other words, the thickness is 1/4 of the wavelength of the light in oil. This is what it is. But I don't need even to plug in numbers yet. If you feel like, you can. So if you feel like, you cannot even calculate the numbers here because you don't know the index of refraction of the oil. They only tell you that the index of refraction of the oil is larger than the index of refraction of water. And this is why we have this lambda prime divided by 2 term. Okay, so the minimum possible thickness that satisfies this condition is when m is equal to 0. So we stop here, and now we solve a separate problem, a second problem, which is formulated in the last sentence of the problem. Now they say that if you have a separate problem, now you shine a different wavelength light, unknown different wavelength light, lambda 1. And you observe constructive interference, bright reflection from this light. Figure out what is the minimum possible wavelength of this reflected light from the same film, of course. And so, in other words, they're telling you that you have a separate problem like this. The same thickness of the film, thickness T, but now instead of red light, you have unknown wavelength lambda 1 that comes in. Again, it gets reflected. It enters, gets refracted, reflected again, and coming here as ray number 2. So when you're inside the oil, the wavelength changes to lambda 1 prime. Equal to lambda 1 divided by the index of refraction of oil. This is N1, this is N2, this is index of refraction. And now let's write the condition for constructive interference, because they say that you're observing bright reflection. So if you have to go, feel free to go. I'm going to finish. It is a single equation that looks like this. Lambda 1 prime, it has to satisfy the following condition. I'll write it right here because there is more space. So this is difference. So you have the optical path difference is 2 times t plus lambda 1 prime divided by 2, or minus. Let's use minus again to avoid negative integers. Has to be equal to, oh, I'm sorry. Look, I missed something here. The first case was destructive interference. They say that you don't observe reflection. So it is m plus 1/2 times lambda prime rather than just m. And the lowest thickness is going to be given with m equal to 0. And therefore, you're going to have, look, lambda prime divided by 2, and lambda prime divided by 2 is going to give you lambda prime only. So you're going to have only lambda prime here for the first part of the problem. The second part of the problem, constructive interference, which means that the path difference of the two light rays is going to be some integer number m times lambda 1 prime. And m can be, the number m could be 0, 1, 2, and so on. And look, probably the easiest thing to do is just to substitute here. They're asking us to figure out lambda 1 prime. Lambda 1 actually. And this is, they're asking what are the wavelengths, lambda 1, that satisfy this constructive interference requirement. And if you substitute here 2t with lambda prime, the red light in oil, you have lambda prime minus lambda 1 prime divided by 2 is equal to the unknown integer number m times lambda 1 prime. And well, they're asking about the wavelength in, not in oil, but in vacuum or air. And you can substitute the primes with, they are equal, right? Lambda prime is the red light wavelength divided by the index of refraction of oil. Lambda 1 prime is the unknown wavelength divided by N2 again. So it is the unknown wavelength lambda 1 divided by N of oil. And here you have, it has to be equal to the unknown integer number times lambda 1 divided by N2. Okay? N2 cancels out everywhere. So again, we want to find lambda 1. And when you put this term to the other side of the equation with opposite algebraic sign, you're going to get lambda, the red light wavelength, is equal to m plus, hold on, so this is, I didn't make the correction here, I have to, this is lambda prime, okay, to t, okay, and here I have the same thing, lambda prime, okay, and so it's going to be m plus 1 times lambda 1. I'm missing some factor of 2. I did not figure it out. Where is it?
Dr. Tatar.
Using
Yeah.
the 1/2, you have 2t minus lambda prime divided by 2.
Here, or
Because, well, you have lambda prime minus lambda 1.
oh yes, this is half. Yeah, this is half. This is a factor of 2. Yeah, so it's like this. And when this lambda 1 divided by 2 goes to the other side, it becomes like this. And now you can say the answer lambda 1 is equal to the red light wavelength in air divided by m plus 1/2, where m could be 0, 1, 2, and so on. Next, you just have to try different values of m until you get a wavelength within the visible part of the spectrum. And this is what your answer is going to be. So just start with m equal to 0. If m equal to 0 gives you wavelength outside the visible part of the spectrum, you go to m equal to 1 and so on until you hit a wavelength that is inside the visible part, and this is what your answer should be. So we're going to stop here. I'm sorry that I kept you longer. Next time, we're going to finish a few minutes early to compensate for this. Have a nice weekend.